All right. So let's see. Today, I guess this is lecture number 17 for our DERs class. I shuffled around the schedule a little bit. Last time we had a bunch of really good questions, and so we ended up discussing things that were a little bit kind of off script, which is great. I love that. But it did mean that we didn't get through the full lecture last week on Thursday. So we will basically finish up that lecture today. I think that'll be like the last half or two-thirds roughly of this class period. And at the beginning, I just want to talk through some logistics, more or less related to the final project. Um, so I guess let me just take a few items quickly off the list here. So one thing, we had gotten some questions from people about sort of the problem number 4 on the midterm exam. So I recorded just a short, I think 8 or 10-minute video about that problem. It doesn't go through all of the exact details of the solution process, but it just kind of sketches out roughly the flow and the main equations that we needed. So no pressure, but if you want more information about that problem number 4, you're welcome to look there for it. And that is on Brightspace. It's not publicly available, but if you go to the Brightspace page and then click content, and then down here, click on guest lectures and student talks. I guess it's not the perfect name for that folder anymore, but anyway, this is where the kind of ancillary videos for the class go. And so you can find it in that folder. I also sent out an email today basically about the formatting for the final report. Um, okay, so I'm just going to walk through that. So I am going to ask that you, probably it's a sort of somewhat non-standard format compared to some undergraduate classes that you might have done project reports in, but I'm going to ask you to use a language called LaTeX, which is basically a typesetting language that allows you to make beautiful documents. It looks a little bit more like writing code than something like what you see is what you get, a WYSIWYG editor like Word or a Google Doc. But it's particularly good at typesetting math equations. So if you have a paper where you need to spell out a bunch of equations that you're using, it can be actually a little bit more convenient. It also just gives you more customization and control over what the final document looks like. But anyway, I feel like working with that, at least for the grad students in this class, is a valuable skill because often the papers that we write and submit to academic conferences and journals are written in LaTeX. So if you don't already have some experience with it, you'll get some experience in this class. So I am also going to ask that you use a particular LaTeX template, basically just a prescribed format for a document, and that everybody basically will write in this standardized template. So if you click on this link, it will bring you to a website called Overleaf, which is basically, it's an online collaborative platform for basically shared documents that are written in LaTeX. So it's kind of like Google Docs, but for LaTeX rather than for like Word documents. So click that, and then you'll come over here. You can click Open as Template. If you don't already have an Overleaf account, you'll be prompted to sign up for a free account. And then it will bring you to a page that looks sort of like this. So I just want to walk through briefly what we're looking at here. So on the left-hand side are basically the source files that are used in this template document. So there's a sample graphic that gets included in the final time set document, which is a PDF. That's what shows up on the right-hand side here. There's some documentation. This is what's called a class. So this is a list of basically commands or aliases that get used in the main LaTeX document. And then over here, I guess this conference 107 something, this is basically the document where all the text shows up. And sometimes helps to make the screen a little bit larger. But all of the stuff that shows up in the PDF over here basically comes from coded commands that show up on the left-hand side. So this command, for example, says, make the title of the paper conference paper title. And that's what shows up over here, conference paper title. And then you can put in the author names and affiliations and so forth. Okay. So that is a little bit about basically how to, or the, I don't know, format that we want the document in. And then the content that should show up for the final report. Basically, I want you to stick to this fairly narrow format here. And this more or less mimics the format that you would have either in an academic paper or in a technical report or a consulting type report. So you begin with an abstract, which is just a high level summary in plain language of what you did. So what problem did you tackle? Why is it interesting? what have other people done? How is what you did different? And then what are the main findings? And you can put some numbers in there. We found that if you can charge and discharge a bunch of batteries at the appropriate time, you can save 20% in your energy bills or something like that. Okay, so this is more or less aimed at, the abstract is basically aimed at giving away kind of all the main findings and the main points of the paper. Then there should be a section that's kind of background and motivations. It's roughly an introduction to the paper. Again, this describes the problem, why it's important, and so on. Sort of the abstract, but in more detail. And in particular here, in a true academic paper, you would spend a lot of time reviewing what other researchers have done. Because one of the challenges of publishing an academic paper is you have to convince people that what you've done is not only interesting, but also new. For this class, that's not necessarily required. You don't have to be the first person ever in the world to have found out whatever you found out. But I think it's still good practice to say, well, there's a Department of Energy report, and then there's a report from a major battery manufacturer, and this utility did something. And here we're doing something that's kind of related to those, but a little bit different. And here's our unique flavor. So you go through that. And then methods, this is really kind of the core of what you did. So here you describe the equations that you used, what data sets you may have pulled from, and you can provide citations here, you can write the equations and so on. If you wrote some code, you can describe a little bit about the flow of your code and so forth. And then the last section here, you go into basically the outputs. So for most people and most teams in this class, I think almost everyone is doing basically computer work. I think one group actually is building some stuff. That's the group that is the terrarium for a lizard group. Yeah, exactly. So I think they're actually putting in some sensors, getting some real data and stuff like that. But for most of us, we'll say, we wrote some code. Here's the equations that we were simulating in the code. Here's the data that we used. And then in this final section here, the results and discussion, you basically say, and then here's what happened. Here are the outputs. And so here you're trying to present a fairly small number, probably in the range of like 3 to 6 graphs or tables that kind of summarize the main findings that you came up with. And so you should spend some time kind of making sure that each graphic is worth the space that you're giving to it and it conveys some kind of an interesting message. So that's the results. And then the discussion is basically like, what did we find? What does it mean? How do we interpret it and contextualize it relative to stuff that other people already know? And what were the limitations? Oh, maybe we used a really simple model of the battery in our work, and somebody else could come in and redo kind of a similar process, but with a higher fidelity model, for example. Okay, and then down here, so please write as clearly and concisely as you can. So in like a high school or even maybe in your college sort of general education requirements, you might have had a requirement that said your paper must be at least 2 pages long or must be at least 10 pages long. And here I'm saying your paper may be at most 8 pages long. And ideally, it will only be 6 pages long. We will actually take points off if it's 7 or 8 pages. And if you go beyond 8 pages, we're just not going to read or grade any of the stuff that shows up. So, so you need to pay attention and spend some time trying to craft the writing so that it is succinct, meaning it doesn't take us a million years to read and internalize and grade. And also clear and conveys the main messages and kind of the value and the quality and the scope of the work that you did. Here's just a link, a nice paper that basically tells you a little bit about kind of nice ways to structure and present the stuff that you do. So 10 simple rules for structuring papers. And this is really about scientific and engineering papers primarily. Okay, and then the deadline for this will be just before midnight on Thursday, May 1st, which is kind of the latest deadline that I can reasonably give you guys and still have time to do the grading. 1 week from then, we'll have to upload the final grades. Some people asked if there's maybe they haven't written a paper in this format before, if they can get help. And I think the best thing to do there is just to come to office hours, either with Nada RTA or with me. So please feel free to use those resources. They're there for you guys. Okay, questions about this? By the way, I have a little quick presentation that gives you kind of a crash course in LaTeX and gives you some starter equations and code and things like that you can use. So I'll go through that in a minute. But any questions kind of about the logistics or the formatting for the final report? Okay. All good there. So I think we can close that stuff. So here I'm going to come over to, there are basically 2 ways that people use to create documents or presentations using LaTeX. And one of them is the software Overleaf that I just showed, which is, again, a collaborative web tool, sort of a Google Docs. And then you can also use an editor on your own computer. So this is a program called TextShop, which is sort of like, I don't know, whatever text editor you might use to create Python code or MATLAB code, something like that, but it's for LaTeX specifically. So I'm now going to walk through some slides very briefly, and I will show you both the output, the PDF output, but also the input sort of source code that shows up there. So, all right, so this is another PDF. It looks quite different structurally from the thing that I showed over here in Overleaf. And the reason for that is that it's a totally different document style and a totally different template. So here, this is meant to be, a 2-column text-based, document. And over here, we're looking basically at slides that we use for presentation. So this is how I make the slides that I present in this class. Okay, so what does the source code look like over here? There's a preamble, basically, where I, say essentially what class of document am I creating? Is it an article? Is it a conference paper? Here I'm using the class Beamer, which is basically how you make slides with LaTeX. I have my own package. This includes a bunch of custom commands and things like that that just make it easier to write stuff. And then we go on to sort of the front matter of the paper. So here we're defining the project title, class, team members, and so on. And that's what shows up over here. All right, so this is actually, in addition to showing you a little bit about how LaTeX works, I actually want to convey some content here. So basically this set of slides, which again, I will share and you guys can customize and play with and stuff on your own. But this basically is designed to show you what the format of the final presentation should look like. Last year, I required everyone to do the final presentation in LaTeX using this Beamer package for making slides. The feedback on that was it was annoying. So I will let you guys use PowerPoint or whatever other software you want to. You're welcome to use this package if you want to kind of learn it, but you don't have to. But anyway, the presentation format should actually roughly mimic the format of the paper. So we should have a background and motivation sections where you basically at a high level summarize what your problem is, why we might care about it, why is it important, interesting, maybe what are some challenges that you found when tackling the problem. You don't have to follow this exact format, right? You're certainly welcome to improvise a little bit, but basically give us some introduction. So here's what that slide looks like. Let me make this a little bit bigger text so you can see a little bit more easily. But here's what basically the code looks like to basically do the typesetting that showed up over here. So this BIT means begin itemize, which is kind of an environment. It's sort of like the scope of a for loop or something like that. There's a begin and an end statement, and the stuff that shows up in the middle is basically a bulleted list. So that gives the bullets here. And then there's another itemize environment here or scope in here. And this is where we have the kind of sub list that shows up here. And then the command /pause is basically how you roll out a slide kind of step by step. So if you have a complicated slide, lots of words or a complicated graphic, sometimes it helps to roll it out slowly so that you don't like lose people or overwhelm people. And then this thing here, big skip, basically just says skip a bunch of vertical white space. Yes.
So when this is exported as a PDF, does that pause say slide 1, slide 2 between pauses, or is it?
Okay, so the question is, when you export this as a PDF, do you export basically a whole bunch of slides? And the answer is yes. So all that pause command really does is it says draw a full slide with only the content before the pause. And then you have another slide after it, which contains that early content, but then also the stuff that comes after the pause. So when I make the final PDF that I put online for the slides that I share with you guys for this class, I basically comment out all of the pause commands. So the % is the comment character in LaTeX. So if you comment this thing out and recompile it, it basically takes out that intermediate slide and it just has the full kind of rolled out content in it. But yeah, good question. Okay, so here, I don't know, I think last semester, again, I required that everybody had to use convex optimization at some point in their project. So I was like, you should spell out your problem statement. Here, you don't have to do that this semester, but I think a lot of you probably will find some use for the optimization material. Anyway, so one of the nice features of LaTeX is that it's pretty easy to write this stuff. And actually, the source code for writing math looks pretty similar to the output that you get. So I don't know, making all of these symbols in PowerPoint, it's certainly not impossible. The final product probably wouldn't look as clean, but for me, it would just take a lot longer to do this sort of, mouse-based picking out all the symbols and stuff like that. So, so I find this more convenient, but your mileage may vary. Um, you can, I'm not sure I would recommend it. I do it all the time, but you can draw diagrams in LaTeX, and the source code for diagrams looks kind of hilarious. So like you literally tell it, okay, I want a thick line, and it should be a rectangle, and it should go from the bottom left corner here at the origin to the top left corner here at the 0.11. And so you literally tell it like every line that shows up in the document, here's how I want you to draw it. I want it to have an arrow on it. I want it to be orange and so forth. So it's a pretty painful way, especially there's a steep learner's curve for learning how to do diagrams like this. I don't necessarily recommend it, but again, once you get good at it, you have pretty much full control over everything that happens in the diagram. It's easy to kind of copy and paste and then make a slightly different version of it with minor tweaks and things like that. So there are advantages to this. Okay. So yeah, you should start with background and motivations. You should state the problem kind of formally, and then you should talk maybe a little bit about related work, assuming that you have time. What did other people do? What did they find? How is your stuff unique or different? And then you should have in your presentation probably a slide, probably not much more than 1 or 2 slides, but about the methods. And here, you don't necessarily have to talk in excruciating detail, but you should give us at least a high-level kind of overview of how you did whatever it is that you did. The paper should have more details to the level where we could, if we wanted to, go in and reproduce your work, write our own code that basically had the same equations and stuff that you used and hopefully gets the same results. But that's not necessary in the presentation. Here, we're looking for more kind of the general shape of things. So here, again, I give some examples of what math looks like in LaTeX. So I'm not going to go through this in detail other than to say, I give you some examples of how to make bold things and, how to put squiggly braces under things with other messages and stuff like that. So if you find some of this formatting useful, you can just basically copy and paste that code and then make a few minor updates. And then, yeah, just a general note, and this is not specific to LaTeX and Beamer presentations, but really, I think all presentations of technical content. It's actually a rather challenging rule, and I break it myself more than I should. But basically, limit the number of equations that you put in your slides, because it's a really easy way to basically get people lost. I think I don't have to convince any of you guys of that, because I'm sure that you have fallen half asleep here. Yeah, there's a lot of stuff going on this slide, right? So this is basically an example of what not to do. But it is possible to go too far in the other direction, by the way. So sometimes you're presenting technical material and you have a very skilled expert audience, and they actually want to see the gory details. And if you don't show them, sometimes there's a perception that, I don't know, that your work is not so deep or maybe not correct or something like that. So know your audience, of course. And then you want to present results. And actually, the results section for the presentations that you guys give should be the main component of what you guys present. So the bulk of the time really should be about this. We want to learn about all the cool stuff that you did, that you found, and so on. And then here's some code for how to make a table in LaTeX. And then, yeah, just so comparing LaTeX to Microsoft Word, I think LaTeX creates elegant, beautiful documents. Word is terrible, of course. The learning curve for LaTeX is unfortunately very steep, whereas it's easy to get started with Word. And LaTeX gets you much more geek credibility. So.
The backside, I just need to take a picture.
Sure. Yeah, so that stands for elite, which is elite. It's like video game nerd speak from like the year 2000. So it's not surprising if you guys don't get it, but for me, that's my wheelhouse. Yeah. You may want to, if you're using LaTeX, or actually in your document, you'll want to include some graphics. So typically what you would do from something like MATLAB is you would export your graphics either in an EPS format or maybe like a PNG or a JPEG. And then in your LaTeX document, you basically include a line that says, I want to include some graphics. Here's how wide it should be. So text width is roughly the width that the text spans on the page. So you might say, I want it to be about 80% of that, or you could make it bigger or whatever. You can also scale by height. That would be /text height rather than text width. And then this is the name of the document, and it's optional to put the thing at the end. So I think this is probably a JPEG, so you could put .jpeg if you want. but the compiler is smart enough basically to look for all the image formats. And here's what it shows up as. So basically this is 80% width. We can rescale it if we want it a little bit wider and recompile here, and it'll grow a little bit.
Do the files have to be in like the right folder, or where like this image file, is it stored with that LaTeX file?
Yes, yeah. So the question is, do the files all have to be in the same folder? And the answer roughly is yes. So typically you'd have like a whole folder for your document. It would have the LaTeX source, which is a few different files. It's the PDF output. It's also a .tex, which is the input file. But also you would, in that same folder, you would dump in whatever images you're including. If that is too messy for you, you can also create a subfolder that has your graphics in it, and you can put all the images in there. And then basically in this statement, you would put that folder inside. So you'd have like graphics slash XKCD or whatever. Okay. Yeah. Okay, and then you can also make backup slides. So this is, I don't know that you guys necessarily need to do it for your presentation here, but if you're giving technical presentations, again, to expert audiences, sometimes people have questions that are kind of side tangents to the main storyline that you're trying to present. But you may anticipate some of those questions, and you look really well prepared if you can have some backup slides basically to address the questions that come up. But you might not want that to show up in your slide numbering and things like that. So you basically can put in an appendix. So you just have slash appendix, and it knows basically to restart the slide counter at that point. And then, so I'll just go through these backup slides here. By the way, I give examples of how to cite things in footnotes and things like that, how to put in links and URLs into your paper. Okay, some important content here. Again, just like I'm going to be a little bit meticulous and probably a little bit annoying about the length of your documents, right? So your project should not be super long and sprawling. We're also going to be pretty strict about timing. So we have a lot of presentations. I think we have 52 students or something like that in this class. Average team size is 2 or 3, so we end up with like 20-ish teams. So to get through all the presentations in 4 classes, we need you guys to be kind of tight on timing. So we're gonna, and in particular, our TA Nada is going to be trying to schedule with you guys for the last 4 classes, basically when your teams will present. But we will also give you basically a time limit to hit. I think it's going to be probably 10 minutes or maybe 12-minute presentation, and then kind of in the 2 to 5 minutes range for Q&A after you finish. By the way, you should, again, just like with the midterm presentations, you should only have 1 speaker. So we don't want to do the thing where the whole team cycles up and everybody reads 1 slide or something like that. So there should be one speaker who tells a coherent story all the way through, but the whole team should be ready to field questions at the end. So if one of your teammates is focusing on the physics and the modeling, and someone else is focusing on the optimization and code, and you get a question, and the presenter, say, is the optimization person, but you get a question about the modeling, then your modeling expert should be able to jump in and field that if needed, right? Okay. When I am making presentations, I try to budget about 2 minutes per substantial slide that I present. So this doesn't count for like, the intro slide or the thank you slide at the end, but anytime there's an equation or a graph or a non-trivial idea that I'm presenting, roughly 2 minutes there. So if you guys have 10 to 12 minutes, you should think 5 or 6 slides basically as a starting point, plus maybe a couple of quick ones. But the main thing, so that's a target to begin with. And then once you have that in place, to understand, what your actual timing is going to be, really the only thing to do is to practice. So your presenter should practice at least a couple of times before you go live in front of the class. I don't know about you guys, but I also when I'm presenting, I speak faster than when I'm practicing. So I usually take off 10% or something like that for the time. This is more an aesthetic thing. This is more my take. Other people have different takes, but I think that presentations tend to be a little bit more easy to absorb when they're less cluttered. So you can simplify, use pictures wherever you can rather than words and equations. Again, I break that rule more than I should. And then if you have a busy slide, meaning a slide with a bunch of text on it or a bunch of equations or just a really complicated graph, again, it can be valuable to roll that out kind of piece by piece rather than sort of throwing everything at the audience together. And then a very common mistake, something that I still do and that my grad students, even the very senior PhD students still do, and it takes constant reminder and constant attention. But basically, whenever we put up a graph, we are always familiar with the graph. We made the graph, we know what it means, we know what all the axes and lines and stuff are. but the audience is basically seeing that graph for the first time. So if you just jump in and say, oh, as you can see here, like, the thing squares exponential or scales exponentially or something, people aren't going to get that, and they're going to get lost, and some people might get annoyed, or they might just tune out and get out their phones or whatever it is. So we want to walk through users, walk the audience members through basically everything that we show. So this starts by showing basically the axes. Here's what's on the x-axis. Here's what's on the y-axis. If there are multiple curves, what do they mean? And then what is the main takeaway that we want you to leave the presentation with? So let me actually demo that with this XKCD graph here. Okay, so if I was presenting this for the first time, I'd say, okay, so this is a graph of the strength of our relationship on the y-axis, and the x-axis here is time, and this spans the day that we first met to today. And so you can see that there's a precipitous decline. There's rising gradually over time. This was the rough patch we had during COVID or whatever. And then here we get to the point where this rapid decline begins. And the audience here says, of course, well, that's when you started graphing everything. And then you say mere coincidence. And then you'd say something like, the main takeaway from this message is blah. I guess XKCD is a good comic. That's the takeaway. Okay, and then, so that's when you're presenting a graph. When you're making a graph, and again, my grad students know this is something that I like hound them about, but making sure that the axis labels are big enough to be legible, the legends are clear, and any annotations that you put, so any text that you put in the slides with arrows and stuff like that, those things can be super valuable to help the audience understand quickly what you're presenting, but you do need to make sure that everything is sort of big enough and bright enough that people can see it. Okay, so I know that was pretty quick. I don't expect you guys to automatically know how to create LaTeX documents, but this will give you a starting point, and then the template that we have on Overleaf is another starting point. And there's lots of people who have done lots of stuff in LaTeX over the years. So you can use generative AI to get you started. You can just Google on Stack Exchange or something like that. You can find solutions to most problems you may have. And of course, you can always come to office hours and work with your teammates and things too. So any questions about, I guess, formatting or anything for the presentation or the document? Yes?
Does the include reference style, or
so the question is, does the IEEE template include a reference style? And the answer is yes, it does. And there are a couple of ways to handle references in LaTeX. You can create a separate file. It's called a .bib file, and that typically has all the bibliographic information. So let me just, I guess, show one thing. So suppose, I don't know, someone's doing battery degradation, something like this. Okay, we want cite a paper on battery degradation. So you can go on Google Scholar and search for that, find whatever paper you're interested in, and then you can click on here, cite. And BibTeX is basically the format that would be used for, this is sort of the raw code that would go into your LaTeX document. So you can just select all, copy, and drop it into your .bib file. And then, so this says, this is an article, this is the handle that I'm giving it. Let me blow this up a little bit. Pelletier 2017 battery. Okay, so this is the author, this is the year it was published, and this is the first word of the title. But this handle here is basically what you would put into your LaTeX source code, not in the bib file, but in the main file for the document. And you would just write /cite, squiggly braces, and then this handle. And then that basically tells the compiler, okay, I'm going to look in your bibliography file for something that has this handle, and then I will build the citation with the appropriate title, author information, and so on. Does that make sense? I know you kind of try it first, but yeah, but that's what I would recommend. Yeah. Okay, good question. Any others? All right. Okay, so for the rest of class here, and we may get out a little bit early. I don't think there's that much content still to present, but I want to basically touch on what we did last lecture and just finish this. So you may remember that. Actually, let me go back to the course outline for a sec. Okay, so where are we? We had a couple of, I guess, 3 sort of eat your vegetable classes where we basically were learning some math about optimization, so that we could. Sorry, I'll stop saying that same joke. In the same way that early on we had a couple of basically background classes here with math and ODEs before we started the simulation and the DER modeling section. So here, again, we had, basically some math background before we jumped into, again, DER applications. So last lecture was our first time basically being back in the DER applications. And we basically just wanted to say, okay, we know a little bit about the sort of the constraints that go into DER models. They come from the dynamics, how the energy state of a battery evolves or how the temperature in a building evolves. But they also come from things like equipment limits, how much power can you put into or get out of a battery, and so on. So we know a little bit about the constraints, but we don't know that much yet about the objectives. And so last week's lecture on DER objectives was basically to say, okay, how do we translate all the economic information that we learned early in the semester about what you might want to do with DERs? How do we translate that stuff into math, and in particular into code that we can give to an optimization solver? Right, so that's kind of what we were doing. We went through a little bit of background on sort of economics, some reminders about vertically integrated utilities versus kind of other restructured utility models. We talked about prices for electricity and what they look like over time and space and different customer groups. And then we went into the section of optimization reminders. So we talked about affine functions, we talked about convex functions, we talked about composition rules for basically building up convex functions from simpler atomic functions. And then we went through linear objectives, and this was things like energy efficiency, energy cost, either with a constant price or a time of use price, a critical peak price, a real-time price, things like that. And then we moved into nonlinear objectives. And here we talked, I guess I'll just go through these quickly. We talked about net metering. So if you're trying to minimize energy cost, but you have a different price when you're exporting versus importing power, you might find yourself in this regime. We talked about demand flexibility and specifically symmetric demand flexibility, which some wholesale grid operators require from DER participants. So this symmetric demand flexibility is basically the minimum, the smaller of either your upward flexibility here, so moving from our nominal power P to our power limit, or the downward flexibility, moving from our nominal power to our lower limit. So take the smaller of those two. In this illustration, it is the upper limit, and so that sets the minimum that shows up here. Okay. And then we talked about peak demand, actually a bunch of different flavors of peak demand with the target demand limit, where you say, oh, I don't just care about the absolute peak, I care about sort of the increase in peak over some target that I have in mind, which could be the peak from this same month last year, or it could be some goal you have of a 10%, 15% reduction. And then we talked about peaks during sort of system-wide or coincident peaks. So the peak that happens at one building might actually not be that relevant to what's happening with the infrastructure needs on the full power grid. We might care more about what's happening when the overall system, which might involve millions of buildings potentially, when that overall system is sort of near its peak. So in that case, we might sketch out the system peak hours and then penalize the highest value during those hours. Okay, and then we wrapped up by talking about load reduction, or what's sometimes called demand response. So this is something that actually it's one of the more common things that people do today. Not necessarily the most sophisticated thing, but a pretty coarse and fairly useful thing, which is during periods when the power grid is really stressed, meaning demand is really high, almost at the limits of what's available on the supply side or in the transmission grid. That during those periods, basically a utility or some other grid operator would send out a signal. And it might be a price signal, but it might just be a directive that says, I would like you to please turn off your air conditioner, or please reduce your load by 10%, or please reduce your load by 10 kilowatts, something like that. So this happens, for example, with air conditioners on hot afternoons in California, where the grid is very tight, and the utility might say, okay, during this period, this say 2 to 8 p.m. window, I need to compress load as much as I possibly can. So I will pay you the difference between what you sort of would have, the counterfactual here, or the baseline, what you would have consumed absent intervention, and then the blue thing here is the measurement, what you actually consumed. And so you can imagine if you had a bunch of buildings, you control their air conditioners, you might pre-cool those buildings, so using more energy than baseline, kind of in anticipation of the peak. and then drift a little bit during the peak window, and then spend a little bit more energy later to kind of recover and pay back that debt of cooling, if you like. Okay, and again, the price during these load reduction windows or demand response windows can be very high. So in California, it's about $2 per kilowatt hour, which is like a factor of 4 to 5 higher than normal electricity prices. All right, so that is kind of what load reduction is and how we specify it mathematically. So it would just be the maximum either of 0 or the delta, basically, between the nominal, the orange baseline here, and the blue, what we actually consume. So if the blue is above the orange, in general, there's no penalty in these programs. If you accidentally overconsume, you don't have to pay at $2 per kilowatt hour. But there is a reward if you curtail, then you get paid. If that makes sense. Okay. So with that formulation, this maximizing the revenue from a load reduction or a demand response program is actually not convex. And so it doesn't fit nicely with our convex optimization tools. And this is actually one of the first ones that we found that we have to be a little bit careful of. Okay, so here's what we want to do. We want to maximize the revenue or minimize the negative revenue. Those are equivalent. And we can write the sort of negative revenue here as negative delta T times the price here, pi hat, which this again might be the $2 per kilowatt hour, times the max either of 0 or of the load reduction. Okay, but if we apply our composition rules here, we find this thing here, max of 0 and the load reduction is a convex function of an affine function. So this is in fact convex. But we are multiplying that by a negative sign, and the negative of a convex function is a concave function. So this means that we are trying to minimize a concave function. So we have essentially a hill-shaped thing, but we're trying to go low on that hill, and that ends up not being a convex optimization problem. So to solve that, there's kind of a simple trick, and basically, instead of solving the true problem that we care about, which does not have penalties, again, for accidentally over-consuming beyond the baseline, we just imagine that there is this like fictitious penalty. So rather than trying to maximize this function here, the load revenue function, or sorry, the load reduction function here, we minimize instead the orange, think of it as an envelope or something like that, but it's sort of the nearest convex function to this thing. So this thing is concave, it has a kink in it, it's sort of hill-shaped. This is the first thing that's actually convex. In fact, it's affine, right? But that's affine is a special case of convex, so that's okay. So basically, all that amounts to mathematically is just deleting the max here and just saying we want to minimize this thing. And so this is, again, introducing this sort of fictitious penalty. But that's okay. We really don't want to be, over-consuming during these terrible hours anyway. So the approximation here then is an affine function of the power. And so that's cool. We can take that and plug that directly in to our optimization. And in general, it will be a non-decreasing function. Okay, and then the last set of objectives here that I want to talk about is what you might call reference tracking. This is a very general problem that shows up in control systems. So if you've taken a controls class recently, probably you've done not just a stabilization problem, but also some kind of a reference tracking problem. The basic idea is that you have some signal that you are trying to track. You have some control actions that indirectly manipulate sort of the measurement that you want to keep close to that signal. Okay, so here we're describing R. This is a vector that has, basically it's a time series with a scalar value. So each of these things would be just a number, just a scalar. But we have it over some time span. And this is basically a profile of energy or power that we want to follow. So we can quantify basically how bad we are missing that profile in a number of ways. So one would be using what's called the mean absolute tracking error. So here we look at the absolute value between the measured power, P, and the desired power profile, the reference, R. And then we basically just add it up over all the time steps in which we're supposed to be doing this tracking problem, and then take the mean. So divide by the number of time steps. And it's not hard to show that this can be written as the one norm of the error signal, which is the difference between the thing that we're trying to track and the actual measurement. So it's the one norm of that error signal, and it has a factor of 1 over k in front of it. Okay, so this is one way to basically quantify the error, how badly we're missing the reference signal. Another way would be using sort of a 2-norm approach rather than a 1-norm approach. And so here what we would do is we would look at the error, we would square it. So this basically says it's bad to overestimate it. It's also bad to underestimate. And so we'd square it so that we impose kind of a quadratic penalty on the error. And then again, we add it up over time. We take the mean. And then at the end of it, this would have units, say if R is in units of kilowatts, this would have units of kilowatts squared. And so to kind of put it back in the original units, so the stuff that we care about, we take the square root at the end. So then this whole thing on the left-hand side here would have units of just kW. And so again, it's not hard to show that you can write this as the 2-norm, but now there's a factor of square root of k rather than a factor of k that showed up out here. And then another way to quantify kind of how badly we're missing would be to use, rather than a 1-norm or a 2-norm, we could use the infinity or the Chebyshev norm. And so here we would look at the error signal and just say, give me the worst element. So this thing is a vector for which each element is the error at a given time step. And this would say, find the worst time step, find the error at that time step. And then that's the value here. So basically this takes the maximum over all the time steps of the absolute error between our measurement and the reference. Okay, and then all of these are convex functions of the power p, because they can all be written as norms, and we know that norms are convex. Okay, so when might we want to do a reference tracking problem with DERs? I think we talked about this example a little bit last time, but there's a service to the grid called frequency regulation. Basically, the high voltage power grid is an alternating current system. In the US, the current waveform and the voltage waveform would fluctuate in a sinusoidal-ish pattern with a frequency, or at least the dominant frequency of 60 hertz. And we talked about how the basic problem of power grid operations is to balance supply and demand. And when supply of electricity, basically your electrical energy, dips below demand, then the frequency on the grid will tend to sag. So it might go from its nominal 60 hertz to 59.9 or 0.99, something like that. So the idea would be, in order to basically regulate the frequency on the grid around that 60 hertz nominal operating point, we would have a bunch of resources. They could be power plants, like a gas power plant or a hydro plant, but they could also be a bunch of DERs, air conditioners, batteries, and things like that. And they would be constantly playing this game where they would get a reference signal, an R, from the grid operator, and that would say, use more, use less. And then they would ramp up or down their consumption kind of in proportion. Okay. So most of the things that we talked about, basically looking back at all the nonlinear objectives that showed up in this section, most of them actually can be reformulated in such a way that they fit into a linear programming framework, and basically by introducing dummy variables and things of that nature. So most of the nonlinearities, not all of them, but the vast majority of them, came either from a max function, so in something like peak demand, or they came from a min function, for example, in the symmetric load flexibility, the kind of ramp up or ramp down, and had a min term in there, or absolute value. So for example, in the sort of 1-norm, the mean absolute error approach to reference tracking, we had an absolute value term in there. And then CVX can do this kind of automated reformulation of those things into kind of a linear programming framework. You don't have to know all the guts and details of how these things work. I just want to mention them briefly to again, explain a little bit about what's happening under the hood with these tools. So if we want to minimize the max of some stuff, and here the X and the Y you could think of as being like the power over time, or the difference between 0 and the power, something like that. So to minimize the max of X and Y, we can actually minimize a dummy variable Z, subject to a constraint that Z is bigger than both X and Y. And you can kind of reason your way through why that might be the case, or you can draw a little picture, but this ends up being mathematically equivalent in the sense that if we solve this problem on the left-hand side, kind of the optimal thing that we get will be the same as if we solve this problem over here. Play a similar game with the max function. and then the absolute value function as well. And I think I actually walked through this back when we were talking about Chebyshev approximation to data fitting. So you can take the absolute value and you can write it as minimize a dummy variable y, subject to y being bigger than both x and negative x. All right, so the upshot of this, the take-home message from this is that most of the DER problems that we want to solve, most of the interesting problems, actually can be formulated with some modeling gymnastics. They can be formulated as linear programs. And that is fantastic news because linear programs are among the fastest optimization problems to solve. There are very mature, robust solvers that we can use. So you're basically guaranteed a good solution in a usually pretty fast time. But there was one objective that showed up that actually didn't have any of these sort of easy nonlinearities, the ones that can be reformulated as linear programs. And this one was the two-norm approach, or the root mean square error approach to reference tracking. So when we're using that one, we need to be a little bit careful. And generally, the type of solver would be a little bit different that would get used by CVX under the hood. Again, not something you need to determine yourself, but the solver would be slightly different for that approach. Okay, so I'm just going to summarize kind of what we talked about last lecture and today. So we have a bunch of objectives, and they all have kind of curvature and monotonicity properties that give us the information that we need in order to understand kind of how to program them in a convex optimization solver or modeling language. So energy efficiency, this is an affine function of the power. Its monotonicity is non-decreasing, so everything's cool. This basically works with all of the different DER models that we have developed. Energy cost, also good. Here the difference between energy efficiency and energy cost is that we put in a price and a potentially time varying price. So if this thing has a positive price, we're all good. It's affine and non-decreasing. We need to be a little bit careful when we get into situations where there may be a negative price, because then our function becomes non-increasing in the power. And depending on the DER that we're working with, that might lead to an error. So we need to be a bit careful. And then we also talked about energy cost when we had the reduced net metering, so a different price for exporting power versus importing power. And that is convex and non-decreasing, which ends up being fine for all of our DERs. We also talked about pollution. So this could be air pollution, greenhouse gas emissions, water pollution, things like that, associated with basically burning fossil fuels to generate electricity. Those things are easy to integrate with any of our DERs. And then we talked about reference tracking error. And we talked about 3 different ways to do that. 1 norm, 2 norm, and then infinity norm. And all of those norms are convex, but they are not monotone in general, meaning they don't have a non-decreasing or a non-decreasing kind of pattern. It really varies depending on the data. So we need to be a little bit careful of those depending on the DER that we're working with. We talked about peak demand, convex, non-decreasing, all good. Upward flexibility and downward flexibility, we need to be a little bit careful with the monotonicity of the downward flexibility. And then the symmetric flexibility had that minimum function in it. And that made it basically not monotone. So depending on the DER and the output function that tells us the relationship between sort of the action variable that we can control and the electric power used or by the DER. So if that function is not linear, then we need to be a little bit careful with this as well. And then we talked about load reduction being a concave function that we want to minimize, which if you try to program that in CVX or CVX pi, you will get back an error. But we can always use this approximation where we basically impose this fictitious penalty for going over the baseline of the counterfactual power use. Okay, so I want to go through an example. Before I do, any questions about this kind of compendium of all the different objectives that we might want to deal with? It's not a totally exhaustive list, but it gets you a lot of the way there. So questions or comments about this? Yep. Yeah, so the question is the homework going to be a little bit more hands-on so that you can get a little bit more feel for how to work with these tools? I guess hopefully the answer is yes. By the way, your homework has been posted. So this is now up. So if you go to the website, you can pull it up. Here we go. So it's actually only two problems, although one of them has several parts to it. So the first problem here basically is a combination of pencil and paper work and some programming. So I give you a function, some example function. It turns out that it is a convex function, but I want you to basically use the composition rules that we learned about in class to convince yourself, to establish that this thing is in fact a convex function. So you'll need to say, okay, well, this has a bunch of exponentials and a bunch of linear functions. So I get some properties from those about decreasing, increasing, convexity, et cetera. And then you can use your composition rules basically to build up convexity of this whole thing. And then you will do pencil and paper work, basically solve what are called the first order optimality equations. The gradient of the function has to be equal to 0. So you'll look at this thing, you'll take its derivative with respect to each of the arguments, write down the gradient. That'll give you a system of equations that you then solve. So this is pencil and paper stuff. And then you will actually, for this one, not use CVX or CVX pi, although you can if you want to sort of verify that your work is correct. But you'll use basically some starter code that I put up on GitHub, which is to implement the gradient descent method. So this, again, is kind of the simplest optimization method for differentiable functions. Basically, you look at the derivative that tells you the direction the thing is increasing in. Take the negative of that. That tells you how to go down with respect to the function. So basically, you implement that fairly simple method, and you should be able to find the same thing, the same that you found up here in part B for x star. Okay. And then problem 2 here is using either CVX in MATLAB or CVX pi in Python. You'll need to either download or import the relevant kind of package. And then there's basically a fairly open-ended battery optimization problem. So we want to do kind of buy low, sell high with respect to a time varying energy price. And so you need to basically, I'm not giving you starter code for this one. You have to create it kind of yourself. And you'll have to draw some plots. You'll have to solve the problem and so on. Not a crazy complicated problem. And we'll do some examples next week in lecture that are kind of similar to this problem. But this, at least, it's kind of like a hello world of convex optimization for DERs. Right. So, okay. Questions about this one? Grant, are you smiling because this is basically the problem that you guys are doing for your project? Yeah. So this will be a good start for some of you guys. And then number 3, I just put it on here. It's not actually going to be graded, but I decided I think it would be cool to have kind of a discussion class. And I think it'll be the last class before the final presentations. So I basically gave you some reading. You'll have 2 weeks to go through it, more than 2 weeks, I guess. And it's about, I think it's like 70 pages total of reading, and then one like 20-minute podcast. But it's like reading a report that's like lots of pictures and big letters and stuff like that. So it should be not too bad to read and go through in the time that we have. But anyway, so first I want you to listen to a podcast, which is basically an interview with the author who wrote the report. The report is by the Department of Energy, has an office called the Loan Programs Office that gives out basically loans for technologies that maybe aren't mature enough yet to get funding from a big bank or a venture capitalist. So that basically they take a little bit higher risk, but potentially very high reward technologies and give government funding, government loans that then get paid back when the company is successful. Anyway, they are interested in DERs and what are called virtual power plants, basically collections of DERs that do the stuff that we were talking about today. Reduce peak load on the grid, provide reliability services like frequency regulation, stuff like that. Okay, so the whole report is basically like, where are we today with this technology? Where do we want to be, and kind of on what time frame do we want to get there? And what are the basic barriers between here and there? And then how do we knock over some of those barriers? And so if you are interested in going to work in a field like this, then I think that kind of report would have some valuable information for you. So anyway, Grant, that was total tangent. I remembered that I wanted to walk through this with you guys anyway, so thank you for the reminder. But yeah, I think there will be at least some more hands-on kind of work in the homework here. By the way, I wanted to point out one other thing. On April 15th, so 2 weeks from today, at least the sort of in-person students, if you want to, we will meet, rather than meeting in the classroom, we'll meet over at what's called the Renew House and the DC Nanogrid House. So these are 2 basically research test houses that my group works with. One is run by Purdue, one is run by Whirlpool Corporation. but they have a whole bunch of the DERs that we talked about in this class. And so you'll be able to see a heat pump and see solar panels and see a battery and all that kind of stuff. Some people I know have already visited these houses, but for those who haven't, it should be a fun opportunity. And we may try to do something like record the whole thing on a phone camera and put it up on Brightspace if people are interested but can't make it in person. So anyway, don't come to class on the 15th. Come to the house instead. I'll put up the address and stuff like that online. Okay, any other questions about this before I show a quick example? All right, so we'll go into this reference tracking example. It's just a few slides. So the problem here, very simple, but imagine that we have a battery, something like a Tesla Powerwall, maybe. Suppose it has 5 kilowatt power capacity, meaning it can charge or discharge at 5 kW, and then 13.5 kilowatt hours of energy storage capacity. So this thing has 2.5 or 3, somewhere in that range, hours of storage capacity. And we'll look ahead over a 1-day planning horizon, and we'll use a 15-minute time step. Nothing special or magical about these things, just kind of made up. And we'll begin, actually, I want to compare the 3 different ways to sort of measure the error or the badness, how much we miss the reference that we're trying to track. So we'll start out with the 1 norm. And the idea here is that we want to minimize a mixture of the energy used by our DER, our battery, meaning we probably have to pay for the energy that we're using. And here we have a time varying energy price. We want to minimize that, but we also want to reduce the 1 norm of our tracking error. So this is the mean absolute tracking error. So we want to minimize kind of each of those and the trade-off between the two. So there may be times when, in order to track the reference, we need to use more energy. So that would help us with respect to this objective, but it would hurt us with respect to the first objective. We'd be using more energy. So kind of the trade-off between those two competing objectives is governed by the energy price over here, and then this price pi t, which I call a tracking error price. So this is how we quantify basically how bad it is to miss the objective that we're trying to track. And then the energy price is it's a 2-tiered time of use rate. So it's just 10 cents overnight and then 2 cents during this kind of peak period of 4 to 9 p.m. And this is just made up, but this roughly mimics both your homework problem actually and also some rate plans that you can find in reality. And then I just manually tuned this price until I got performance that looked pretty good. So I started with a small price and I said, we're prioritizing energy efficiency too much and we're not prioritizing the reference tracking enough. So then I increased the price a little bit until it looked like it was a pretty good balance. Okay, so I'll show you first the 1 norm or the mean absolute error tracking results. And then I will also show you the results for the other, the 2 norm and the infinity norm tracking problems. And in order to have a fair comparison between the 3 methods to really showcase kind of the influence of how we measure the missing of the reference that we're trying to track, I constrained the energy cost. So this term here, I said in the 2 norm problem and the infinity norm problem, I said that it had to be the same as what we got in the 1 norm tracking problem. So we're kind of controlling for the energy cost. We're saying the total amount that you pay for energy is the same no matter which way we do the tracking problem. And then we end up just in the other problems, we only have the 1 objective left over. So we don't need a price. We just put in the tracking objective. Does that make sense? Okay. All right. And then in all of the examples, basically, I say you have to leave the battery no worse than you found it. So if you begin with a lot of energy in the battery, you have to end with that same amount of energy. Otherwise, you just get these weird results where you basically leave it with 0 at the end, sell off all the energy that's in the battery. And of course, time doesn't end when our optimization horizon ends. In reality, we'd like to probably do this the next day. And so if you leave yourself with a full battery, you're kind of screwing yourself over for the next day of operations, basically. Okay, any questions about the setup here? Okay, so here are the results for the 1 norm tracking error problem. So let me walk through this graph with you guys a little slowly. First of all, the x-axis in each of these figures is time measured in hours. So this is a 1-day span going from midnight to the next midnight. The top plot is showing the power, either charging or discharging. So if it's at here 0, we're doing nothing. Above 0 means we're charging. Below 0 means we're discharging. And the shaded period here is the high price period. So this is where we go from 10 cents a kilowatt hour, kind of in the off-peak period, to 20 cents a kilowatt hour during the peak period. And then the dashed lines just represent the capacity of the battery. So this is negative 5 kW is the hardest we can discharge, and 5 kW is the hardest we can charge the battery. And then the dashed line in the top plot is the reference signal, the thing that we are trying to follow, basically. So perfect tracking means that the black line sits exactly on top of the red line. Okay, so the top plot is electrical power. The bottom plot is the chemical energy that is stored in the battery. So this is basically the state of charge. This is 0 down here. So I think we don't want to go below like 20% battery. So this is whatever 20% of 13.5 kilowatt hours is. And then this is the max 13.5 up here. So you can see that we're gradually depleting the battery over time. And then we fill it all up completely before this peak period. And then we basically dump all of that energy that we just put in. And then we begin to track again. And you can see that the initial energy state of, I don't know, maybe 8 kilowatt hours is the same as the final state. So we're succeeding with that constraint that we imposed. Yes.
What's the real life meaning of the reference again?
Yeah, so what's the real life meaning of the reference? So this would show up again probably in like a frequency regulation problem. And so if we went to MISO, the headquarters is about 45 minutes away. We drove down there and we talked to them. They would say, yeah, this is one of the services that we pay people for, is frequency regulation. So we send out a signal every second or 2 seconds, and we say, use 10% more power, use 15% less power. And it's typically varies in this kind of sinusoidal fashion. And that's used to basically do this continual balancing of supply and demand. So that's kind of what we're emulating here. In reality, we'd be using like a 1 second time step, not a 15-minute time step for that problem. But this shows roughly kind of the shape of the problem. Does that make sense? Okay. So yeah, you imagine this is kind of a command or an instruction that you're getting from a grid operator. And then the black is what you're actually delivering. Okay, so what happens here is fairly intuitive, I think. You basically, you just perfectly track the reference signal more or less forever, basically boring behavior, until you get within about 3 hours away from this peak window. And then you say, oh, okay, if I can fill up the battery here at low price, and then dump all that stored energy here at high price, I can make some money. So we fill the battery, and then we dump the battery, and then we get back to just reference tracking. And at the end here, we do a final kind of diversion deviation from the reference in order to basically refill the battery to meet this constraint that says you have to end with a full battery. Or anyway, the same amount of energy that we started with. Okay, so I think the 1 norm results are fairly intuitive. The 2 norm results here, I'm showing again the same plot. And we have the same constraints. Final energy has to equal the initial energy. But I also constrain the energy, the total amount that we pay for energy to be the same as what we paid in the 1 norm problem. And so the objective here is basically just to track this stuff. And so you can see it's a little bit different behavior. So if we flip back and forth, broad strokes is pretty similar. We do kind of a pre-charging the battery and then a discharging during the high price period. We do a similar thing here, but actually it's kind of spreading that charging out a little bit longer. So rather than just kind of 3 hours in advance, we're going back 5 or 6 hours in advance here. Also, it's not perfectly tracking the reference during all of these periods. And then again, the final sort of refilling of the batteries is spread out a little bit as well. And then the discharging, again, is not just done during the first hour or 2 of the high price period. It's actually spread out a little bit more. So let me just ask, we'll talk in a sec. So if we show the infinity norm here, this is where things get a little bit weird. So the infinity norm is it's a worst case thing. So here we're saying what we care about is only the largest absolute deviation that we have from the red curve and the black curve. So it doesn't actually care during this period whether it's tracking the signal or not, because basically what it cares about is kind of the worst case, the furthest deviation. So anyway, it does like a weird thing, not tracking the reference at all, basically just using 0 power during these periods. It also discharges the battery here, which is a little bit weird. And then it does a little bit of a sort of pre-filling the battery and dumping the battery here. And then we go back to sort of not tracking at all. And then final plot here, these are histograms of the tracking error. So the difference over time between the reference signal, the dashed red line, and the measurement, the black curve. And so this is the one norm error. So on the y-axis, so the x-axis here is the error, the tracking error, and on the x-axis is the tracking error, and the y-axis is basically how many time steps, how many of the 15-minute bins basically did that tracking error fall in this range. So you can see with the one norm, overwhelmingly, we are at 0 tracking error. So basically perfect tracking for much of the time. But we do have occasional big tracking error differences that either were way above or way below the target. And that's basically happening during this period here, where we say, you know what, I don't care about the tracking objective for this period. It's so valuable to do the price arbitrage, the buy low, sell high thing, that I'm just going to prioritize that. I'm just going to buy low at kind of as hard as I can, and then sell high kind of as hard as I can here. And then we get back after that's done, we kind of switch back and we go back into reference tracking mode. So that's where these errors, positive and minus, show up in there. For the two norm reference tracking problem, we get something closer to sort of a bell curve shape in the tracking errors. And again, we get fairly large deviations here. So we go down to maybe negative 4.5 kW of a maximum error. And then for the infinity norm, you can see that the sort of tails here, the left and the right hand tail, have been sort of chunked down. They've been knocked down into a shorter range. So the worst case tracking error is only about 2.5 kW, either on the plus side or on the minus side. So sort of the worst miss is the best from the infinity norm, the one that explicitly is trying to minimize the worst miss, if that makes sense. Okay, so staring at these three plots again, like which one of the one norm, two norm, or infinity norm, which one just qualitatively to you looks like the best? Which one would you be like, this system is behaving correctly or better, the best of the three? So who thinks it's the one norm, the first plot here? 3, 4 people. Who thinks it's a two norm? So 2 or 3, 4 people. Okay, so roughly tied. And are there any votes for the Chebyshev norm? Yeah. It's just not the appropriate way to measure the error for this problem, right? It just leads to totally weird behavior. But I think, yeah, either the one norm or the two norm would be a perfectly reasonable way to kind of quantify missing here. For me, I don't know, I kind of like the behavior of the one norm. Like it sort of just has this like, it goes to extremes. It's like either I'm going to prioritize the tracking problem and just do that perfectly, or I'm going to like put that on hold and I'm going to do the energy arbitrage problem and I'm going to do that perfectly. It sort of flips between these two extremes. Whereas the two norm is kind of a milder, it's like doing a little bit of both at all times. So I don't know, aesthetically or philosophically, I guess you can draw your own conclusions there. Okay, so that's all for today. Any questions about this stuff? Yes.
Sorry, going back to the equation, maybe I missed it. You divide by k in the one norm example. Do you not divide by the square root of k for the two norm?
Yeah, so the question is, up here in this example, I divided by k in order to turn the one norm into the mean absolute error. There's this factor of k difference between those two. And then your question was, why didn't I do something similar for the two norm or the infinity norm formula? So if we go back to our norm slide, so a little while back, the root mean square tracking error has this floating factor of square root of k. The maximum absolute tracking error actually doesn't have that factor in it. But like, why did we leave out the square root of k factor down here? And that's actually a good observation. That's a fairly subtle point. But the idea is if you're minimizing some function f of x, that's equivalent to minimizing a function a times f of x, where a is some positive scalar. So a could be 1,000,000 or 1.3 or whatever. So you get the same answer. You get the same optimal value, the same best power profile, regardless of whether or not you include sort of that positive scalar. So yeah, I guess I could have put the square root of k in here, but the result would be the same. Now, when would keeping that square root factor in have mattered? If we were solving the kind of combined, the two objective problem, where we had the energy and the tracking in the same function, then if I left out this floating factor of k, we get a different sort of balancing of the two trade-offs between the energy performance and the tracking performance. Yeah, that's a good question. Thank you. Any other questions or comments? Yes.
Like for all of our optimizations, is it acceptable to have kind of a function factor in like your alpha that we're tooling with like give it some human touch?
Yeah, so the question is, in your optimization, if you're using it for your final project, is it okay to keep like a tunable parameter in there that you can fiddle with a little bit in order to reshape sort of the output of the optimization? Absolutely, like almost without fail in any sort of real practical optimization problem. The first time you specify and solve the problem, it's just like very likely will not give you the performance that you actually want. And so you'll probably need to go back in and say, oh, actually, I care more about this thing than I thought I did, so I'm going to put some additional weight on that. Or, oh, maybe this formulation wasn't exactly what I wanted. It turns out my objective is slightly different, so you go back and change that. But yeah, absolutely, you should feel free to have tunable twiddly knobs that you leave into your problem and then mess with them until your performance is good. Yeah. And that's the same, like if you guys have taken a control design class, there's always gains and stuff that you fiddle with until your performance is similar or is appealing or attractive. So yeah, very, very common and totally acceptable. Yep. Any other questions or comments? All right, then thank you guys, and I'll see you on Thursday.